Hey, and welcome to this video about the domain name system in my Networking Basics series. I'm Wolfgang Tremmel and I run the DE-CIX Academy. For more content or the rest of the series, just check our website, go to decix.net/academy and find the videos page. Good, let's get started with the presentation. Networking Basics is about explaining to, well, not that technical people how the internet works. I had quite a number of webinars or videos already, starting explaining about what is a network, about Ethernet, about the IP protocol, and all the protocols who contribute to the internet experience. And this is now part 6a actually of the series, and I'm going to talk about the domain name system, a quite important part of the internet. So let's get started. If you think back some time and think about your old grandma's telephone, well, it might have looked like this. And these telephones, even today, they just use numbers, telephone numbers. And if you want to call someone, you need to know his or her telephone number. And if you do not know that number, you have to look it up somewhere. And yes, it was a printed phone book. You might still have these, you might still know these, but today, well, they kind of fell out of use. So what we need is a kind of a phone book for the internet. Let's talk about the network layers, the IP layer. And you remember the webinar, the video about IP protocol. It also just uses numbers. It uses IP addresses. And IP addresses look like this: IPv4 with the numbers and the dot, and that's actually not an IP address there. That's something with a digit too much. And IPv6 addresses, they are even longer. They are impossible to remember and even quite impossible to read out. So what we need is an easier way to use the internet. If you think of your web browser, you do not type in IP addresses. It's way too complicated. You'd want to type in names like www.decix.net. So what we need is a phone book for the internet which translates these names to IP addresses. Well, a phone book which translates a name to a number. If you think how easy this could be, well, just make a text file with two columns. On the one side you have the name, on the other side you have the number. And actually that's how it started. And this file was named etc hosts, and it still exists on a lot of systems today under that name. If you're working on a Mac or working on a Linux system, check out your file system and you will find a file named etc hosts. But it's quite some time ago when this file finally reached 7,000 entries, so 7,000 systems connected to the internet in the 1990s, there was a need for something better, something new. And the solution was, well, what do you do if a text file isn't sufficient anymore? You use a database. And in this case, it even using a distributed database. And this was the domain name system, and it was finally specified in 1987. That's how old it is. The work even began earlier. The first drafts exist from 1983. And the whole idea behind is have not a single flat column or table with all the entries, have a tree-like structure. And this is what we are using today. It is tree structured. It has domain names which have a part and which are hierarchical. So the original top-level domains, they were ARPA, COM, EDU, gov, mil, and org. And with that, you can see, or you can deduce who sponsored quite some of the development. Well, there is .mil in there, which stands for military. The country domains, like we have them today, like .de, like .uk, they were also specified, came very early. .net, which is in use today, came a bit later. And the German top-level domain .de, that was registered in 1986. And if we talk about the domain name system, the system itself, which does the translation, how does it fit into our protocol stack? Well, DNS uses UDP as a transport protocol originally, so it builds up on UDP. TCP is also possible, that was added in 1987. UDP and TCP are both on the transport layer. So if something uses the transport layer, well, it must be application layer. So DNS belongs to the application layer, but other applications on that same layer depend on it. New standards for DNS domain name system even use HTTP, yes, the same protocol you're using to browse the web, as a transport protocol. And there is also a definition using secured connections, the transport level security. But that's quite new development, and I want to talk about the principle of DNS now. So the principle of DNS, you have to start with DNS over UDP, how it was originally defined. If you remember the video about UDP, you know that there are port numbers in UDP, and for DNS, the well-defined port number of 53 is used. Originally, the idea was that DNS packets have a maximum size of 512 bytes to avoid any fragmentation. So if a packet is too big and a link only allows smaller packets, it has to be fragmented, so cut in two and set together at the target again. And you wanted to avoid that, so the definition was have the maximum size 512 bytes. But today, and even for quite some time, larger packets are possible, and they might be fragmented. That's the problem sometimes. And talk about DNS. It was invented just to translate names to numbers, but a lot of stuff was added to DNS. And I'm not talking about all of that. I mainly talk about how it translates names to numbers. So how does it work? How does DNS get you, if you type in a name, an IP address? And so the first thing I'm explaining is how DNS queries for an IP address. So let's have a look at that setup, which might be the same setup you have at home. You have your laptop, which is connected to a router in your basement, which connects to some internet service provider, which connects you to the internet. And you type in, you wanted to know DE-CIX.net's website, so you're asking for the IP address. And what your laptop does, it sends a DNS request packet to your local router. Your local router runs a piece of software called a DNS resolver, and which does nothing else than to forward or to resend that question to your ISP. When your router connects to the internet, it gets the IP addresses of the resolver of the ISP, of the DNS software of your ISP. It gets it advertised, and so it knows where to send that query. So it now sends that same question to the DNS resolver at your ISP. So your ISP also might not know the IP address of that website. So what does it do? It cuts this request in pieces. So it ends with .NET. So the first thing it knows, because it's predefined in its software, where to ask for .NET domains. So it asks the root name server. Root name server are the very top name servers. Where can I get information about the .NET domain zone? And the root name server replies with an IP address. And now the resolver at your ISP needs to ask, where do I get DE-CIX.net? And so it asks the name server for the .NET zone where to get DE-CIX.net. The name server for the .NET zone again answers with an IP address, and now the resolver knows where to ask for www.DE-CIX.net, and that's the name server for the DE-CIX.net zone. And finally, with the third question now, it gets the IP address of the DE-CIX web server. And it caches that answer. So if the next question comes for that same name, it already knows the answer and doesn't have to ask again. So that's the idea of caching built into DNS. If you do not know the answer, you have to ask several times to get it. But once you have received the answer, you remember it for a certain time. And it delivers back the answer to your router at home, which delivers back the answer to your laptop. And your router at home also caches that reply for a certain amount of time. So this is how DNS works, how DNS resolves a name resolves an IP address from a name. And what have we seen here? We have seen here two modes of operation of DNS. One is the recursive query, which is, I want to know an IP address, just give me the result. And that's used by your computer and also your router. So it just asks the next name server if it doesn't already know the answer, if it doesn't have cached the answer. And the other mode was the non-recursive query. So where do I have look next? Going step by step, collecting the answer from a number of name servers. And that's used by your provider's resolver. And usually, well, DNS resolver have to do both, but your little Fritzbox at home usually just asks your provider. So what have we seen here? We have seen that it is hierarchical. The DNS system is hierarchical and it is distributed. So not every name server has every answer, so it asks around to set the answer together. Let's talk about zones, DNS zones. So what are zones? A zone is a unit of authoritative information. So like the zone DE-CIX.net. This is a DNS zone, and in an easy way of speaking, it's just a table of everything belonging below DE-CIX.net. And over that zone, a domain name server has complete and authoritative information. So what this name server knows about the zone, there is no second type of table, no other version. It's the one version of that zone and it's authoritative. In reality, a zone is basically really just a text file with names and IP addresses in it. What is different to etc hosts? Well, that this is all distributed. It's all split up in little zones into name servers all over the world. It doesn't have to be a text file. It can also be a table in a database, especially if you talk about large name servers serving multiple or a really lot of zones. Just think about the name servers for a whole country like .de. And each zone has a so-called primary name server. But well, of course, each name server can serve multiple zones. So let's talk about how does a zone file, how does a zone records look like. And this is if you really have a look at the text file stored on a name server. This is really how it looks like. And these types of entries we have. Each zone starts with a so-called SOA record. And SOA means start of authority. And these values, these numbers here are very important for how the name server deals with your zone. So I'm explaining them. The first example, of course, is the zone name. Here we have example.com, and then we have a value called time to live. And this is the time. You remember the caching when asking recursively. This is the time the entry is cached. And after that time, if there is another query, it has to be refreshed. Then we have the name of the primary name server, and there can only be one, so it's in the header. This entry is actually an email address, and that's the email address responsible for the zone. Just think the first dot as an @ sign, so this is hostmaster@example.com, and this is the responsible contact for the zone. Then we have a serial number. The serial number is important because it helps the name server to keep track of changes. Of course, you can watch the text file and make a diff and have a look if something changes, but it's way too resource intensive. So the name server just looks at the serial number, and if you want to have a change, you have to increase the serial number, otherwise the name server doesn't pick up the change. And for serial numbers, it has always to increase. It's up counting, you cannot go back. So of course you can start with 1 and then go to a 2 and 3, but you might want to add a little bit more information to the serial number. So the best practice today is to encode the date. So if you have a look here, 2021 1102 and the first change on that date. So that's the best practice currently for serial numbers. Next value is called refresh, and that's how often the secondary name servers will pull the primary name servers for changes. Remember I said there is only one primary name server, but that may go down. And who to ask then? So this is the reason for each zone there is normally a number of name servers which have all the same information, and the other name servers are called secondary name servers. And what they do is from time to time they copy the whole zone from the primary and are also available to other name servers for queries about that zone. So every 24 hours the secondary name servers contact the primary for a refresh. Modern software use a kind of a notification mechanism. So if the primary makes a change, it automatically notifies the secondary, which then pull the zones. That's how it is done today. But the refresh value is still there. So every 24 hours, the secondary name service refresh the zone. Yeah, and it's a good idea to place your secondary name servers into another network. Talk to someone. There are also commercial services for secondary name servers. Otherwise, if you have a really bad outage and all your name servers are no longer reachable, you are dead. Your whole zone is no longer reachable. That happens to a quite big network a few months ago. So place your secondary name servers someplace else. You can have quite a number of secondary name servers. Usually 2 to 5 is a good number, and place them at another part of the world and definitely into another network and not your own. Next value is called retry. So if the secondary name server cannot contact the primary, this is how long it waits until it tries again. Then we have expire, and that's also if the secondary name servers cannot contact the primary, how long it will keep the copy of the zone as valid. And you can easily make this 2 to 4 weeks or so. No. And minimum, the last value, that's the default time to live value for entries. Time to live is also the time entries are kept in a cache, and usually that's 2 days is quite a reasonable number here. And you can lower that if you plan to make changes in the future. You can lower it in advance so the changes go through more quickly. Remember, the primary isn't queried if the entry in a cache hasn't expired. So if you make a change in the primary, it might take some time until it is picked up all over the world. I'm using 30 minutes for my own domains here because I play around a lot. Next entry types in your zone file is the DNS entry, and that lists all the name servers, primaries plus secondary. All the name servers which can be queried for your zone are listed as NS entries in the zone. And as I said, we already know the primary name servers from the ZOA entry, but it has to go also here into an NS entry. And the requirement for most top-level domains are that any zone must have at least 2 name servers. Well, I said up to 5, no problem. You just have to find someone who hosts them. And that's what I said before. They are called secondary name servers. And they also must be, of course, registered in the parent zone. So like in .de or .net. Because remember how the query model works. It asks the .net name servers for a name servers for your domain. And of course, it returns then not only one, but all of them. So you can check if one of them is not reachable, you can try the others. Finally, we go to IP addresses. So this is how names are actually mapped to numbers. The EN in the file stands for internet. When this whole thing was defined, there were other networks around, so they put in the EN for internet. A records are IPv4 addresses, and they thought, well, IPv6 addresses are 4 times as long, so we have 4 A's for IPv6 addresses. And if you see here on the left side of the table, there is just the host name because the name of the zone is automatically appended here. So in your zone file, you just put in the host names. You don't have to repeat the name of the zone. So this is how it's done. That's the whole magic. What else can we do with name servers? Well, email was very important and still is very important. So, and you're also using email addresses which contain a domain name. So a mail exchange record is also into DNS. That's the so-called MX record. And here I put in the name of the zone on the left-hand side, and MX10, the 10 is a priority value, so lower values means try first. And on the right-hand side, I can give the name of a host which accepts email for that domain. And that doesn't have to be in the same zone. It can be any host name on the right-hand side which accepts email for you. There is a possibility to put an alias, to put a nickname into a zone file. That's the CNAME record. And here we see the example, paul.example.com has the nickname Peter. And yeah, you can do that. Yeah, so now we know how to translate from a name to the number. You just query a resolver and ask for an A record or a quadruple A for IPv6 record, and you get back the IP address. And this works either with the resolver having the information already in its cache or recursively queries the next resolver or gathers the information itself from the network. But what about the other way around? How can you get from an IP address, you want to know the name of it. And this is called reverse mapping. So getting the name of an IP address is called reverse mapping. And this also works with DNS. And for that, there are special top-level domains defined for that. And that's in-addr.arpa for IPv4 and ip6.arpa for IPv6. And also we are using a special record type. We are using the PTR. That's short for pointer record type. So how does it work? Well, on a very top level, it's quite easy from a user standpoint. You just use, in Linux, you can use a command line command, for example, dic-x, and you get the name, so the tool will work for you. But what's actually queried? How does it really work? And I'm going to show you. So this is what you query. And if you have a look at an IP address, that's actually the most important part is on the left side of the IP address. So that's hierarchical. But if you have a look at a domain name, the most important part of a domain name is on the right side. So what we are doing is we are swapping the IP address around. So the most important part of the IP address goes on the right side, and we are querying basically for the IP address just turned upside down or right side left. And this is what we are querying. 136.121.31.46 if we want to query the name for the IP address 46.31.121.136. And it's returned, named, in this case, myserver.example.com. So keep in mind that it's the other way around, but usually, don't you worry, some tool is doing the work for you. Yeah, and that's what I said. The hierarchy of IP addresses, most significant part is left, and on domain names, the most significant part is on the right-hand side. For IPv6, well, that looks rather long. In IPv6, ip6.arpa is used, and each possible digit has its own hierarchic level. So it's really long query for the reverse mapping of IPv6. Best practice, if you run your own domain, well, do reverse mapping and automate it. Have some tool to build your reverse zones. And also, if you have a forward entry, match the reverse. Not all reverse entry need to have a forward entry. Keep that in mind, especially for network infrastructure. Your router might have a lot of interfaces which have a lot of IP addresses. Having reverse names for all of them is quite nice, but you don't have to match them forward as well. So let's talk about DNS today. That was how DNS works, the history, and But today, like I said, a lot of stuff was added to DNS over the time. Let's talk about technical aspects first. So, of course, every ISP, every internet service provider offers DNS resolvers for its customers. So if you are a home user, well, your router automatically picks them up and you do not have to worry about anything. You just connect your router, you just to connect your laptop to your router and everything works automatically. If you are unhappy with your ISP, there is a number of so-called public resolvers available from a number of providers. There is one from Google, from Cloudflare, from Quad9, and there are more. Just have a look at Wikipedia, for example. Why would you choose one of them over your provider's resolver? Some of them have additional functionality, so they claim they protect you from malware. Of course, Google is so generous to make your a public resolver, and of course, they are using what people are querying for their own statistics, and so does everybody else, including your ISP. Nobody is spying on you, just to make that clear, but the information they can get out of these resolvers are quite valuable to see what people are looking for. All these resolvers use an anycast structure. So if you do not know what anycast is, I have a video about that. Just have a look at the DE-CIX website. And recently, DNS over HTTPS was defined. So yes, the protocol you're using for browsing can also be used to do DNS query. And the idea behind that is not sure if it's really a better user experience, but at least it's more control for the people supplying the DNS. Another technical issue of DNS, of course, there are attacks against DNS. And to prevent a number of attacks, DNS-CIX is a recent extension to make DNS more secure. DNS-CIX is a way that you cryptographically sign your zone files with a public key infrastructure, so that the resolver receiving an entry can really verify that it is correct. Keep in mind, a lot of things are cached, and how does the end user, the computer of the end user, know that the answer it gets from the cache is really the same like in the primary web server? And for that, a cryptographically checkable signature was used or is used. And so resolvers can check the correctness of entries. And this is mainly to prevent an attack called cache poisoning. In cache poisoning, an attacker tries to inject wrong entries into a resolver by sending out false replies. Just imagine a resolver queries an IP address and somebody else fakes the answer before the real answer arrives. And this is called cache poisoning. On a non-technical aspect for DNS, DNS is so central to the function of the internet that it is quite often used as an instrument of censorship. So to suppress unwanted content or to control what people can see, well, just go to the ISPs and forbid them to resolve certain names, and that's happening. And keep in mind, there are public resolvers, and hey, you can also run your own resolver, and if everything goes wrong, you can still put entries in your etc hosts file. Just saying. And yeah, that's it. That's my talk about DNS, domain name, system, and just to repeat what we have learned today. This is always the slide at the end of my presentation. Please remember the following. DNS, the domain name system, it matches names to numbers, like DE-CIX.net to that IP address. The whole domain tree, it's hierarchical and has a tree-like structure, and it doesn't have to end here or even there. You can make it as long as you want. You can add as many subdomains as you want. So there is no need to put everything below DE-CIX.net. You can also have frankfurt.dekix.net, put stuff into there, and so on and so on. And on the top level, below the root, that's the top level, is actually the one below the root, there are domains like .net, .org, .de, and there are many, many more. A number of years ago, the IANA responsible for the whole running of the DNS decided to open up the top level domains. So have a look at your provider. There is a lot of top level domains you can choose from. On the second level, there are domains like DE-CIX, so DE-CIX.net or example.com. And on the third level, there are often already the host names like www.dekix.net. But as I said, you can make this longer. You can put the host name on the fourth or on the fifth level. No problem. Also, keep in mind, DNS is used to reverse map IP addresses back to names, like mapping this IP before address to its name. And DNS is a quite complex system. This talk here just covers a little bit the introduction to DNS. You can talk about DNS a whole week and you haven't covered everything. So have a look at the material. If you download the slides, have a look at the material at the end. There are some pointers to more documentation. Okay, and that's it. And with that, I say thank you for listening. I'm Wolfgang Trammel, and this is the DE-CIX Academy. Thank you. See you next time, and bye-bye.